Hi everyone, I'm Babak. Today I'll be talking about bias in the context of decision support SQL queries. This is a joint work with my advisor Dan Sushu and Johannes Kirk from Microsoft and two undergraduate students from UW, Corey Cole and Peter Lee. Decision support SQL queries are used today by knowledge workers to make better and faster decisions. However, inexperienced workers can easily write SQL queries that are biased for decision making, unless they are trained statisticians, which is not typically the case. As we will see throughout this talk, SQL queries are typically biased and insufficient for decision making, and therefore they would lead to incorrect business decisions. Let's start with a motivating example. Suppose a company has many business travels from four particular airports and would like to choose between business travel programs offered by either American or United Airlines, depending on which one has a better performance in terms of on-time flight. Therefore, the decision here depends on the answer to the question that which airline has a better on-time performance. To find out, the knowledge worker does some simple data analysis. Here, she writes a SQL query that computes the average delay, once for American and once for United Airlines. The bar diagram on the left shows the result of this simple query. You may acknowledge that this scenario is repeated over and over in industry today. Users write declarative queries, explore the results, and make decisions based on the insights obtained from these results. In our example, the knowledge worker look at the bars and observe that American looks significantly better, so she decides to contract with American. However, any trained statistician would recognize that to make decisions regarding the performance of the two airlines, one need to look into additional factors such as how frequently these airlines operate at different airports. Simply because one airline may have several flights from an airport which has a high rate of weather-related flight delays. This makes the comparison between the two airlines with that simple SQL query biased and unfair. This is actually the case in our example. Once we break down the delay by each airport, it turns out that in each of them, it is actually United Airlines that performs better. This trend reversal is known as Simpson's paradox in statistics and happens because of overlooking the so-called confounding variables. The fact that people initially think such sort of reversal are paradoxical shows human judgment is governed by causal knowledge. It is ridiculous to conclude that American Airlines has an overall better performance in the four airports, but in each of the airports it is United which performs better. Indeed, decision-making requires causal knowledge. In this case, what the company really wants to know is the causal effect of choosing American or United on the delay of its travelers. But the simple SQL query fails to answer that question because it is biased. Therefore, the correct investigation that the trained statistician would do includes a causal analysis on data, which in turn includes a complex construction of the underlying causal model to collect the confounding factors and to control for them. What we have done in this project is that we perform this complex causal analysis automatically on top of the structure of the declarative SQL query. Our ultimate goal is to make causal inference accessible to non-statisticians. Similar to the other project that we have seen so far in this talk, we leverage the declarative nature of the query on the database to perform very high-level and complex analysis under the hood. More precisely, the problem that we looked into in this project is the following. Given a group by SQL query used for decision making, we detect whether it is biased for decision making, we measure and report the bias, and we repair automatically the query to remove bias. More specifically, we propose HypDB, the first database system which detects, explains, and removes bias from SQL queries. Instead of discussing the technical contributions of HypDB, I'll demonstrate how it handles the biased query from flight data. Okay, so HypDB accepts as input a SQL group by query and assumes that the query is being used for making decisions. Here, with the simple group by query, the goal is to find out the effect of choosing one of the two carriers or airlines on flight delays. As we have discussed, the answers to this naive query, they suggest that American Airlines performs significantly better. However, HypDB takes advantage of the declarative nature of SQL and performs some deep analysis on the SQL query and automatically detects confounding factors that are detected today only by trained statisticians. These confounding factors make the query biased for decision making. Specifically, first, HypDB warns the user that further grouping by some of the confounding factors would radically change the insight obtained by the original SQL query. As you see in this case, HypDB automatically identified origin airport as a confounding factor, such that further grouping by origin totally reverses the trend obtained by the original query. The next step is to remove the bias from query. HypDB does this by rewriting the query to control for the confounding variables. The query shown right here in this box is the rewritten query associated to the group by query we started with. Please refer to the paper for more details about this query rewriting, but for the moment note that under certain assumptions, the insight obtained from the answer to this rewritten query are unbiased and support decision making. The bar diagram here shows the answers to the rewritten query right here on the left. The answers reveal that it is actually United Airlines which performs better than American Airlines. So there is no Simpsons paradox anymore. Finally, HypDB generates two kinds of explanations for the biased query. We argue that these explanations are crucial for decision making and reveal illuminating insight about the domain and the data collection process. HypDB generates coarse-grained explanations by ranking the detected confounding factors in terms of their responsibility for making the query biased. In this case, as you observe here, origin airport has the highest responsibility. Indeed, more than 50% of the bias is due to origin airport. But there are other factors such as flight departure time that we need to account for, simply because some airline may have more flights during rush hours than the other airlines. And finally, the fine-grained explanation generated by HypDB is essentially a ranking system which drills down into a particular confounding factor and explain how the interaction of the ground levels of the attributes involved in a SQL query contribute to the bias. In this case, the top four fine-grained explanations for origin airport indicate that United Airlines frequently flies from airports such as Rochester Airport that has a lot of weather-related flight delay, whereas American Airlines frequently flies from airports such as McAllen Miller that has fewer delay. And this simply explains why the initial SQL query that we started with was biased toward American Airlines. The second experiment, I'm going to use adult data sets from the UCI repository, which includes attributes such as demographic information and job-related attributes such as hours per week for 50,000 individuals, along with their income that is recorded as a binary attribute denoting whether an individual income is high or low, where high means more than 50K income per year. Actually, using this data set, several prior works in algorithmic fairness have reported gender discrimination based on a strong statistical dependency between income and gender in favor of males. Now to replicate these results, let's use HypDB to compute the effect of gender on income using this simple group by query. Let's do that. As you see right here, the results of this simple SQL query indeed suggest a huge disparity against females. But not surprisingly, HypDB detects that this query is actually biased, and there are other confounding variables such as marital status and occupation that we need to account for. First, HypDB warns the user that further grouping by marital status would radically change the insight that we obtained by the naive SQL query. As you observe right here in this bar diagram, these two bars, they essentially show that there is no significant difference between the males and females' income, but for single individuals, the gap is still huge. Next, to remove the bias from the initial SQL query, HypDB rewrites the query to control for the confounding variables. Here you see the rewritten query associated with the naive one that we started with. In this bar diagram, you see the answers to this rewritten query. As you observed, the rewritten query answers, they suggest that the disparity between males and females is not nearly as drastic as suggested by the naive SQL query. To see what's going on here, let's check out the explanations generated by HypDB. The coarse-grained explanation, they show that marital status account for the most of bias, followed by the occupation. Let's take a deeper look into marital status and see why it makes the query bias. The top 4 fine-grained explanations reveal a surprising fact. They say there are more married males in adult data than married females, and marriage has a strong positive association with high income. To understand why this is actually the case in adult data, we check the provenance of this data set, and it turns out that the income attribute in adult data, it reports the adjusted gross income as indicated in individuals' tax forms, which depends on filing status. It could be actually household income. Therefore, adult data is essentially inconsistent and should not be used for investigating gender discrimination. So, although this dataset does not meet the assumptions needed for inferring causal conclusion, we show that following the correct methodology for drawing causal conclusion, it is still illuminating and reveals something about the data collection process. With this, I will conclude. So we've discussed that SQL queries can be biased and misleading for decision making. We proposed HypDB, the first database system to detect, explain, and resolve biased SQL queries. We saw with 2 examples that HypDB is useful for making causal analysis accessible to non-statisticians, avoiding false discoveries, and also detecting errors in data collection process. Thank you for listening, and I hope to see you soon in Seattle.